Hello everyone. Today we'll be talking about how to measure the magnitude of dead space. In previous lecture, you understood how to derive Bohr's method of dead space calculation and Enkhoff's modification. You also understood the various terms used in these equations, that is P alveolar CO2, mean P alveolar CO2, P arterial CO2, P end expiratory CO2, and P end tidal CO2. So how do you measure anatomical dead space? Let's take an example of normal capnogram. Normal capnogram does not have any alveolar dead space. So the area in red is your anatomical dead space and area in the blue is your alveolar ventilation. VD by VT, in this case only anatomical dead space is present, would be equal to the red area divided by the total red plus blue area. You know that in a normal capnogram, your P arterial CO2 would be approximately equal to P alveolar CO2, which will be equal to P end tidal CO2. If you draw a horizontal line so that area of this rectangle is equal to area of this rectangle, that line will represent P end expiratory CO2. And the difference between the P end tidal CO2 and P end expiratory CO2 would give you the proportion of anatomical dead space. If you are dealing with alveolar dead space, here we are assuming there is a uniform emptying and the time constant of alveoli is the same. So you will get a horizontal phase 3. Your area in the dark red will represent alveolar dead space. Here this horizontal line will measure up to P end tidal CO2, which will be equal to mean P alveolar CO2. However, the P alveolar CO2 in the normal alveoli would be much higher and will be approximately equal to P arterial CO2. So VD by VT would be sum of this whole red area divided by red plus blue area. Alveolar dead space would be represented by the difference between the P alveolar CO2 and P end tidal CO2. If you divide by the total P alveolar CO2, you will get the alveolar dead space fraction. We can see in this diagram right here is if you have dead space, both the alveoli are emptying simultaneously. So the P alveolar CO2 is being diluted by the air from the dead space. This is your end tidal CO2s in this case. If you did not have any alveolar dead space, the P alveolar CO2 would be not diluted by any air, and therefore your P alveolar CO2 will be equal to P end tidal CO2, and therefore your dead space fraction will be 0. To measure the total dead space, you have to figure out your P end expiratory CO2 similar to the Bohr's equation. If you expire your tidal volume into a bag or a ventilator and measure the average CO2 in that air, that will give you P expiratory CO2. The other way to calculate it would be if you can draw a line where the area of this rectangle equals area of this rectangle. That should give you your P end expiratory CO2. In this case, your VD by VT, that's total dead space, will be equal to P alveolar CO2 minus P eCO2 as given by the Bohr's equation. This can be divided into two components, your alveolar dead space, which will be your P alveolar CO2 minus end tidal CO2, that's shown in red, and your P end tidal CO2 minus P end expiratory CO2, that will give you your anatomical dead space. We will use the ABC from the previous lecture. We got P CO2 of 50, which will be approximately equal to the P alveolar CO2. On capnogram, P end tidal CO2 was 30. That should be equal to mean P alveolar CO2. And on the ventilator, you can get your P end expiratory CO2. So your alveolar dead space fraction shown in red will be your difference between P arterial CO2, which is equal to the P alveolar, and you subtract the end tidal CO2 from it and you get 40%. Anatomical dead space fraction will be the difference between your end tidal and end expiratory CO2, that is around 10%, and the total dead space will be sum of these two. Usually you are interested in alveolar dead space, so measurement of end tidal CO2 is very important. The problem comes when the emptying of the alveoli is not uniform, as in COPD patient, and now instead of a nice looking square waveform, now you have a shark fin. Here again the same principles will apply. Your VD by VT will be equal to the total red area divided by red plus blue area. The question is, how do you figure out the red area? So there are two things that we need to know. First, where is our mean P alveolar CO2? Remember, mean P alveolar CO2 was the average of CO2 in normal alveolar ventilation and dead space alveoli, and if you average it out, you should be getting mean P alveolar CO2. Whenever you have a shark fin, your end tidal CO2 and mean P alveolar CO2 are not the same. The second thing you need to know is, where does the phase 2 end and phase 3 begins, because you don't know about what part would be your anatomical dead space and what part would be your alveolar dead space. So let's figure out how to calculate mean P alveolar CO2 and transition between phase 2 and 3. If you extrapolate a line on phase 3 and phase 2, you will intersect at point A, and the midpoint of A and B will represent your mean P alveolar CO2. To figure out the transition phase between 2 and 3, you have to draw a vertical line FE so that the area of this triangle is equal to area of this triangle, and this portion would now represent phase 1, phase 2 and phase 3. So that shark fin can be converted into more squarish looking waveform where we have mean P alveolar CO2 and now we have a vertical phase 2. So this portion, that means your P alveolar CO2 minus mean P alveolar CO2, would represent your alveolar dead space, and mean P alveolar CO2 minus P end expiratory CO2 would represent your anatomical dead space. The second method is a little bit more intuitive. Here you draw similar extrapolating line in phase 2 and phase 3. As before, you draw a vertical line so that the area of these two triangles is similar, and this will represent your anatomical dead space. If you draw another vertical line so that area of this trapezoid is equal to the area of this trapezoid, that would represent your alveolar dead space. Therefore, you should be able to get your physiological dead space, alveolar ventilation, and your total tidal volume. If you want to read more about how to get these lines, please read the references. So how do you calculate dead space using this method? We draw these two lines. We draw a vertical line to get these two triangles having a similar area. That will be your anatomical dead space. If I will draw a vertical line so that the area of these two trapezoids look similar, that will be your alveolar dead space. And if you measure it out, you should be able to calculate your anatomical dead space fraction as this distance, that is 1.8 centimeter, divided by total of 10 centimeter, that is 18%, and the alveolar dead space will be this distance divided by total distance, and the total dead space fraction will be equal to this distance divided by the total distance. Clinically, you are more interested in knowing alveolar dead space, so it is important to measure end tidal CO2. You don't have to get exact numbers, but approximate area of dead space should be good enough. Following dead space fraction in obstructive lung diseases is more objective than reports of subjective changes in wheezing. Anatomical dead space usually remains similar but can be manipulated in certain situations, which we'll talk about in another lecture. So in summary, if your phase 3 is horizontal on capnogram, you can use the end tidal CO2 from that and P arterial CO2 from ABZ to calculate your alveolar dead space. If your phase 3 is not horizontal, that means your mean P alveolar CO2 is not equal to P end tidal CO2. So you have to find mean P alveolar CO2 by drawing the horizontal line by extrapolating phase 3 and see where it intersects with the line of phase 2 and finding its midpoint. Following alveolar dead space fraction can help you know if your COPD or asthma patients is improving. If you really don't want to do calculation, P arterial CO2 minus P end-tidal CO2 can give you a rough estimate of alveolar dead space. The calculations would not be accurate if your phase 3 is not horizontal, but this is better than nothing. Thank you.